Right, well, relative motion. Problem 70 is a 1D relative motion problem. And if you look in the book, the textbook on the section of relative velocity, they'll give you an equation which works. I'm going to show you how to do this problem with the equation, but sometimes, often actually, especially for 1D motion problems where they're a little more conceptually simple, you can just sort of logic your way to the solution. So actually, I'll show you both ways and show you how they work. But sometimes you might want to just use the equation they give you and go from there. I didn't really use it in the next problem, problem 78, for the two-dimensional one, but anyway, I just want to show you that the equation is valid, but usually you can logic your way through it. So, got a river. These are the banks of the river, or the shore. So the river is like in here, and this is land out here. Got a boat. First off, just a couple things about a couple definitions. Upstream is against the current. And downstream is with the current. So we got a boat in the river. Beautiful boat. It is going, I forget, upstream. So let's say upstream is this way at 14 kilometers per hour, which means if it's going upstream, it's going against the current. The current is going this way, and the river flows at 9 kilometers per hour. Alright. So, yeah, that's all they give us. Part A and B kind of go together. What are the magnitude and direction of the boat's velocity with respect to the ground? So let's logic through it first. So if you're standing on the ground here, and there's someone in the boat, how fast does the boat look like it's moving relative to you? Well, if this is a lake, a nice calm lake, then it'd be 14, right? Because it's the 14 relative to this is 14 relative to the water, which means the water looks like, pretend the water is the ground essentially. So like you're probably standing on a floor right now, right? Not moving, and so you're moving at speed 0 relative to the ground. If you start walking at 5 meters per second, you're going to be, I should say running, you're going to be moving 5 meters per second relative to the floor, right? Same thing with the water. Assume the water is still, then you'll be moving 14 kilometers per hour relative to that. So anyway, if the water was still, that means the water and the ground aren't moving relative to each other. So 14 on the water would also be 14 on the ground, and that's what the person on the shore would see. But if the river starts flowing this way, then it sort of cancels out some of the boat's motion because they're going against each other. It would be opposite if they were going in the same direction, or downstream. Instead of canceling out, they would add together, right? So the 14 and the 9 cancel each other out, and the person on the shore sees the difference, which is 5 this way, upstream. Another way to think about it, what if the boat was going 9? What would the person on the shore see? They would see that the boat is not moving anywhere, because the 9 going this way and the 9 of the river flowing this way cancel each other out, and the boat makes no progress, at least relative to the shore. So that's the way to logic through it. But what about using the... Oh, so the answer logicking through it, logicking, is 5 kilometers per hour upstream. That's both the magnitude and direction. Story. Let's use the equation that the book gives us. That equation is VPA equals VPB plus VBA, where P stands for a particle, basically the thing you're looking at moving, which in this case would be the boat. A stands for frame A, and B stands for frame B. So in this case, A might be the ground, for instance, frame A, and B might be the river. So we're trying to find the what is the boat's velocity with respect to the ground. So we're going to define for parts A and B, which we already got the answer for logically. We'll define P as the boat, that's like the particle, and we can call that B. We'll define, well, do I want to, that's going to be confusing with frame B here. Let's call it XYZ. So X. Let's call A, frame A, the ground. And we'll call that Y. And let's call frame B the river, and we'll call that Z. So that equation turns into this: V X Y equals V X Z plus V Z Y. So this, in words, this is the velocity of x with respect to y equals the velocity of x with respect to z plus the velocity of z with respect to y. Or using these words here, the velocity of the boat with respect to the ground equals the velocity of the boat with respect to the river plus the velocity of the river with respect to the ground. Alright, so we know, what are we looking for? We're looking for the velocity of the boat x with respect to the ground y, right? So we're looking for this one. We know the velocity of the boat with respect to the river, that's with respect to the water, 14 plus, and we should probably define, as we always do, direction of motion. The velocity of the river with respect to the ground, that's the flow here, that's going to be -9 because it's going to that way. So it looks like the velocity of the boat with respect to the ground is 14 minus 9, which is positive 5 kilometers per hour. Exactly what we got here, because positive is upstream, so these agree. The positive is upstream. So, yeah, not too bad. What about parts C and D? C and D. In this case, we get a child in the boat who walks from the front to the rear, so the child goes back this way, I guess you could say downstream, right? And we're looking for the child's velocity with respect to the ground. So let's pick, let's make the child the particle. So P equals child, and we'll call that X. let's say A, and I'm only doing this so you can use the equation in the book. Maybe this is not the best way to show you this, but changing all these variables, but kind of makes sense to me now anyway. Let's make A the ground again. Call that Y, and let's make B, in this case, the boat. We'll call that Z. So the equation Vxy equals Vxz plus Vzy. In words, this is the velocity of the child with respect to the ground, which is what we're looking for, equals the velocity of the child with respect to the boat, which they give us is 6. So I'll just fill this in as we go. 6 plus the velocity of the boat with respect to the ground, which, hey, we found over here. Look at that. And I actually forgot something. You probably are yelling right now if you see it. If not, you're like, what? But which way is the child going? Whoosh, that way, negative. So this is actually -6 plus 5 from what we found in part A. So that equals -1 kilometers per hour, or 1 kilometer per hour downstream. So yeah, and that's it. Not too shabby. The next one though might be a little more tricky for you to wrap your brain around, but once you get the hang of them, they're not too bad. So we'll stop there.